Welcome to Engineering Mathematics. Today we are going to do the mesh analysis and solve it in matrix form under the CRAMERS rule. So given this figure here, whereby the current always originates from the positive to the negative in this direction. So whenever current travels or moves in a direction from positive to the negative, from negative to the positive, the voltage will be negative, or rather the current will be negative. But in its normal form, moving from the positive to the negative, then you label it positive. So given this figure here, we want to solve it using CRAMERS rule. So to form a matrix, we'll have to determine the direction of the current. So the current 1 will be moving in that direction, the current I2 will move in this direction, and I3 will have it moving in this direction. So by matrix inspection, we are going to label them into columns 3 by 3. We are going to form a 3 by 3 matrix, so thereby we are going to label them into 3 columns and 3 rows, then form a matrix. Then we solve that matrix by using the CRAMERS rule. So we are going to start with the Z11, then following the row we'll have the Z12, then Z13. So the second row will have Z21, Z22 and Z23, then Z31, Z32 and Z33. So the diagonally, all the values of the diagonal are positive. That's what you should know. Others may be negative or 0, but all the diagonal currents will be positive. So after you have arranged this way, you start by analyzing each loop one by one, and the resistance contained in each loop. For instance, this first loop we have 2 ohm, 3 ohm and 4 ohm. So Z11 will add those resistors in the first loop. So we'll have 2 plus 3 plus 4. So that one will be in the part of Z11. So for Z12, so the common between Z1 and Z12, so the common is only 3 ohm that is shared with Z11 and the loop 2, the loop 1 and the loop 2. So because it enters through the positive side, we label it negative. So this one we label negative. So going to there is no current shared between the loop 1 and the loop 3. So because there is no current shared between the loop 1 and the loop 3, you label it 0. So in the next row, we look at the impedance shared between loop 1 and loop 2. So there you have negative 3. So you label it negative because it moves in the opposite direction. So then for the Z22, you have to add all the impedances present in the loop 2. So you'll add 6, that's 3 and 4. There you go, we'll have the impedances, total impedance in loop 2. So what you should know is that all the impedance in the diagonal should be positive. So for Z23, you look at the impedance shared between loop 1 and loop 2. We have 6, but in the negative direction. Going to the third row, you will have 0 because there is no impedance shared between loop 1 and loop 3. And for the Z32, you will have negative 6 because we have 6 being shared in the opposite direction. But for the Z33, you'll have to add all the impedance present in the loop 3. Therefore, we'll have 4 plus 6 plus 5. So then you solve it to be that way. Then you label for the next bracket, or rather the next matrix. You label I1 the first row and I2 for the second row and I3 for the third row. So, and for the next, that's for the results now across the equal sign, you will have to add the voltages in each individual loop. Loop 1, I3 will have the voltages in loop 1, I1 will have the voltages in loop 1, I2 the voltages in loop 2, and I3 the voltages in loop 3. So for loop 1 we have voltages, we have only 10. We have only 10 as the voltage present. So there across the equal sign, the first row that will have 10 as our answer. So going to the loop 2, we don't have any voltage present. You can see we have the resistance, we have the resistors, but no voltage source present, therefore we'll have the 0. So going to the loop 3, we have 12 volts. We have 12 volts and it's traveling from but the current is traveling in this anti-clockwise direction. So as you can see, it's traveling in an anti-clockwise direction, so we have to label it negative, so it will be negative 12, and this one will be the complete matrix. So we want to solve this one using the CRAMERS rule. So as we said previously, by applying the CRAMERS rule, you have to find the determinant of the main matrix, then find the determinant of individual matrices of I1, I2 and I3. So to get for I1, you have to represent the first column with the values across the equal sign. For I2, replace the second column with the values across the equal sign, and for I3 that column with the values across the equal sign. So this is now how to find the values of the first one. So how to find the values of the first matrix of the main matrix. So I'll have it as 1971. So this now is for the first the main matrix. So going for I1, you have to replace the first column with the values 10, 0 and negative 12. So I1, which will be this one, 9, you replace the 9, negative 3 and 0, therefore we'll have there as 10, 0 and 12 after replacing 10, 0 and negative 12. So this one, after solving this one now, we'll have the determinant of the I1. So after getting the value, you have to divide it with the value of the main matrix. So solving this, will have 21, 24 as our answer. So I1 will have as 21, 24 divided by the main matrix determinant, will have it as 1.077 amperes. So now this one will be the value of the current of I1. For I2, by doing the same, you have to replace the values in the second column with the values across the equal sign. So you'll have that to have 10, 0 and negative 12. So solving for the determinant of this one, So by using the formula of finding the determinant, we'll have negative 198 as the answer. So I2 divided by the main matrix will have I2 as negative 0.1 ampere. So for the I3, the same, you have the main matrix as it was before, then you have to do away with this that column and replace it with the values across the equal sign. So therefore we'll have it as 10, 0 and negative 12. To solve it, we'll have our answer as 1656. So I3 will be 1566 divided by the value of the main. We'll have it as negative 0.840 amperes. So now those are the answers of individual I1, I2 and I3. So from the mesh analysis of these given diagrams, we have been able to obtain I1 as 1.077, I2 negative 0.100 and I3 negative 0.84. So but negative current cannot be represented or given in a negative sign. A negative sign is just to show that maybe the current was traveling from negative to positive side, but during representation you have to represent all the currents in positive or with a positive sign, because they cannot be represented with a negative. So therefore we'll have our I1 as 1.077, I2 0.100 and I3 as 0.840 amperes. That's all are positive. So we can therefore find individual currents in every resistor. For instance, in 2 ohm we'll have 1.077 amperes through the 2 ohm resistance. So through the 3 ohm resistance you will have I1 minus I2. So I1 minus I2 to have the current passing through the 3 ohm resistor, therefore we'll have it as 0.977 amperes if you subtract. So the current through the 6 ohm resistor is I2, so we'll have it as 0.100 ampere. So the current through the 6 ohm resistor will be I2 minus I3, so therefore we'll have it as 0.74. so for the current through the 4 ohm we'll have it as 0.840. that's because it's I3. Then for resistors below the loops we will use individual currents I1, I2 and I3. Pleasure.